Hi there, Coach Travis here, and we've got another problem about how the derivative shapes the graph of the function. All right, so this problem, they're giving us the graph of the derivative. Okay, they're giving us the graph of the derivative, and they're asking a question about the graph of the original function. So be careful. They're asking a question about something that we don't see. What we see in this picture is the derivative, but the question is about f, the original function, f. So at what values does f have a local maximum? So we need to find the local maximums. So again, the mistake is if you said -1 and 1. Because you might look at this picture and say, oh yeah, -1 is a local maximum and 1 is a local maximum. But wait, those are local maximums for the derivative function. They're the local maximums for the function I can see. But the question is asking for the local maximums of the function that we can't see. So don't make that mistake. Okay, so how am I going to do this? The way I'm going to do this is, like I do all these problems, is I'm going to make number lines. So, all right, so I make a number line for the derivative function, and that's where I'm going to be spending most of my time because that's the function that I can see. But I'll also make a number line for the original function, because everything that happens down here with the derivative is going to have a reflection in the original function. All right, so but anyway, we'll worry about the red number line later. So right now we've got the number line for f prime. And so what I mark on the number line are the critical points. So remember that so maybe I should write that down. We mark the critical points. The critical points, those are the places where the derivative is 0 or where the derivative does not exist. And so the derivative is 0, the derivative function. The derivative function is equal to 0 at -1. So yeah, and equaling 0 is the same as having an x-intercept. So basically when I ask when is the derivative 0, that's the same as asking what are the x-intercepts of the derivative function. So the derivative is also 0 at 1. And the derivative is also 0 at 2. So those are the critical points. So those are places where the derivative is equal to 0. And now what that does is that chops the number line up into 4 regions. And the idea is that the derivative function is either always positive or always negative on each of those regions. So as an example, we see that on the region where x is less than -1, the derivative is always below the x-axis. And below the x-axis means negative. And then let's see here. And then between -1 and 1, again, the derivative is below the x-axis. So that means negative. And from 1 to 2, the derivative is below the x-axis. So that means negative. And then finally, when x is bigger than 2, the derivative is allowed to be above the x-axis, and that's positive. And so, okay, so I've gotten all the information I want from the derivative. And again, this is a good question. Why did I do that? Why was I interested in when the derivative is positive and when the derivative is negative? And that was because of this fundamental fact here that I'm using all the time. When the derivative is negative, then the original function is decreasing. Oh, okay, so what that tells me is that's telling me that whenever the derivative is negative, the original function is going down. So I'm going to draw a down arrow. Here, the derivative is negative, so that means the original function is going down. Here, the derivative is negative, so the original function is going down. And here, the derivative is positive, and when the derivative is positive, then the original function is increasing. So now the function is increasing. So the idea here is what we did is we used the derivative. We looked at the derivative and we looked for where the derivative was negative and where the derivative was positive. And that allowed us to say when the original function was increasing and when the original function was decreasing. So the idea, one way to think about this is this looks really scary. This looks really complicated when you first see it. You might think, oh my gosh, this is a really hard problem. But the secret is that if you're looking at the derivative and you want to make predictions about the original function, the only thing you really care about is you do not care about the details. You do not care about all the little ups and downs. All you care about is where is the derivative below the x-axis and where is the derivative above the x-axis. So there's a lot of stuff here to distract you, but all you really care about is where is it below the x-axis and where is it above the x-axis. Because that's what allows us to say where the original function is increasing and where it's decreasing. Okay, so now let's draw our conclusions. So we were asking for where does f have a local maximum? Okay, so a local maximum would be, if I think about what a local maximum looks like, a local maximum is going to be when the function changes from increasing to decreasing. So I want to see an up arrow followed by a down arrow. And okay, this is a down arrow, but then there's another down arrow. Here's another down arrow, and then a down arrow followed by an up arrow. So I think this was a trick question. I don't think this function has any local maximums, because again, what I need to see in order to see a local maximum, I need to see an up arrow followed by a down arrow. But I never see that here. I see a bunch of down arrows and then an up arrow following a down arrow, but that's not what I want. So this guy was kind of a trick question. This guy has, it should have no local maximums. So let's check that. And yeah, that's right, none of the above. So, well, it goes through an explanation there, and I guess you can read it if you want. But I like our explanation here, that a local maximum is gonna occur when the function is increasing and then changes to decreasing. And we analyzed our function and found that that never happens.